theme, prediction, performance prediction. My name is Niels Pinkwart from University of Berlin in Germany. I'll be chairing this session. We have 3 full research papers in the session. One of them nominated for the best full research paper. And what no one really predicted was that the authors would be unable to come here to present their work. So the first work from Carnegie Learning, CMU, and the University of Georgia will be presented in form of a screencast that was prepared by the authors for us. So instead of having a live talk, we'll be having a demo video or video done by the authors that will last for 15 minutes. We won't have really time for discussing with the authors because of time difference, etc. So we will have 15 minutes to possibly discuss about that paper, and followed by a second presentation, which will be from Belgium. And now is the question, is a presenter for the third paper in the room now? So hopefully that's gonna happen. Anyway, so we'll have the video first, and it's gonna play.
Hi, I'm Steve Van Saley. And I'm Steve Ritter. We're going to talk about using embedded formative assessment to predict high-stakes test scores.
This is joint work with Wobo Zhang and Yan Tan of the University of Georgia and with April Galliard of Carnegie Mellon University. We're very sorry that we aren't able to join you in sunny Australia, but we hope that we can convey the work well in this video. We started this line of work thinking about how we can change the way high-stakes assessment is done in schools. School systems need a fair way to understand how teachers, students, and schools are performing, and the United States and other countries have moved to a system where standardized tests play an important role in the system. But standardized testing has taken over to the detriment of learning. Students spend an enormous amount of time on testing, and even more time preparing for the test. This is stressful for students, and the public has strong doubts about the value of all this testing. A recent public poll found that only 6% of the public believed that standardized tests were a good measure of school quality, as compared to 36% who thought that about teaching things like cooperation and problem solving, and 25% who valued technology and engineering classes. As a result, parents have been rebelling. In some U.S. states, parents have the right to withdraw their students from standardized testing. On the left, you see opt-out rates for standardized tests in Long Island, New York, where I grew up. The dark areas represent districts where more than 50% of students opted out of this standardized testing. On the right are similar data from Minneapolis, Minnesota. In that city, over 60% of 11th graders opted out of standardized tests. Clearly, something needs to change. There is another way. It's called dynamic testing. And it's not new. Buckingham talked about it in 1921. The idea is that students are evaluated as a natural part of their everyday schoolwork. This embedded formative assessment improves instruction. It also allows students to progress to the next topic and even the next course when they are ready. There's no need to stay in a course until the test. If you can proceed faster, go ahead. Our Mathia intelligent tutoring system is currently used by over 500,000 students per year in the United States. Although it is an instructional system, we believe that it can also be used to implement a new type of accountability system, one that doesn't rely on high-stakes testing. The Mathia software is implemented as part of a blended instructional system, including text-based activities that are implemented in small groups and the individualized Mathia software. In a typical implementation, students would use the software 2 days a week as part of their regular math class and do the text-based activities the other 3 days. Students can also access the software outside of class, though this kind of usage varies from school to school. Before we talk about our study, here's a short introduction to Mathia. The system is mastery-based. Students proceed to the next topic at their own pace. In addition, the system picks problems for each student depending on that student's strengths and weaknesses. No 2 students receive the same path through the software. As an adaptive system, Mathia is continually evaluating students to determine what they know and don't know. Over the course of a school year, students may spend 40 or 50 hours using Mathia and master hundreds of skills or micro-competencies. Through this usage, the Mathia software gets a very complete view of what students know and don't know, perhaps better than any standardized test can do. Problem tasks are constructed to ensure that students show each step of their problem-solving process, similar to students showing their work. For example, in this problem, students describe the quantities being related and the units of measurement. They define a function relating the two quantities, and they answer questions about this relationship. In order to answer these questions, they solve equations. This helps students develop an understanding of what the equation means and why solving an equation is useful, not just the mechanics of how to solve an equation. Our cognitive model not only tells a student when they've made an error, but also diagnoses why they might have made that error. It's really important to distinguish between a careless error, like using the wrong variable, and a fundamental misunderstanding of the mathematics. The cognitive model also represents, for each topic, a fine-grained understanding of what each student can do and what that student has yet to learn. This model is expressed in the scalometer. You can see that this scalometer is distinguishing between problems with positive and negative slopes and those with positive and negative intercepts, and also between problems which express quantities as words, such as FIVE versus the numeral phi. The particular skills assessed are validated based on data and are different, of course, for each topic. As students complete a problem, each step is associated with one or more skills, and those skills will go up or down depending on whether the student gets things right or wrong and whether they ask for hints. In standard assessments, students can't ask for help. In Mathia, they can. But since we know when students ask for help, we can take that into account in assessing what students know.
Other researchers have considered the problem of using process data from learning platforms like Mathia to predict standardized test scores. Our approach is informed by our previous work in predicting scores on the Virginia Standards of Learning, or SOL exam, and an exam used in West Virginia using data for several thousand learners who used Mathia and its predecessor, Cognitive Tutor. The data we used were gathered from over 23,000 learners over 3 academic years in Miami-Dade County Public Schools in the U.S. state of Florida. There, students use Mathia as a part of a program called iPrep Math, an innovative approach to blended instruction and collaborative learning for students in grades 6 through 8. Over the course of the 3 academic years, from 2013-2014 to 2015-2016, Florida used 2 high-stakes end-of-year tests, the Florida Comprehensive Assessment Test and the Florida Standards Assessment. To predict scores on these tests, we consider previous year test scores, process measures from Mathia, and socio-demographic factors. Mathia process measures include counts of micro-competencies mastered, the rate at which students master material within the program, and a variety of transformations of these and other variables detailed in our paper. Socio-demographic features include indicators like exceptional student status and an indicator of socioeconomic status. Following our previous work, our analysis approach seeks to delineate the relative contributions of different categories of variables to the predictive models we construct. We begin with relatively simple models, including only a pretest score or only Mathia process variables, and subsequently consider different combinations of these variables with socio-demographic variables. These data are inherently hierarchical, as students are nested within classes, and classes are nested within schools. However, it is possible that we could do well enough without considering this structure. We consider both types of models. There is also a question as to the complexity of the statistical approach that is required to achieve satisfactory performance. We consider both the relatively simple approach of stepwise linear regression and a more complex approach that is random forest regression. We rely on typical evaluation metrics within the literature, considering both mean absolute deviation and root mean square error. To rigorously test our models, we learn them on data from a single year, for example, the 2013-2014 school year, and then test them on data from the other 2 years. We first consider models that do not take into account the hierarchical nature of this data. We compare stepwise linear regression to the random forest regression approach. On both evaluation metrics, stepwise linear regression consistently outperforms the random forest approach. While the data on this slide are for performance on the training set in the 2013-2014 school year, we see the exact same pattern when the model learned for the 2013-2014 school year is applied to data from subsequent years. This slide displays results for stepwise linear regression models trained on 2013-2014 data and applied data from subsequent years. achievement levels are typically distinguished by 10 to 15 points. Root mean square error values, as well as mean absolute deviation values, are below or within this range. The important takeaway from these results is that there's a great deal of promise that our models, at worst, can be expected to provide predictions of a student's achievement level within one level of that predicted by the FCAT or FSA. Models M1 and M2 are minimal in the sense that they rely only on pretest scores or only on process data, respectively, and perform comparably on held-out test data to the best models reported in our previous work, as well as those reported by Pardos and colleagues for assessments on held-out test data. This indicates that the process data from Mathia is nearly just as predictive as the pretest data from an equivalent standardized test, but the combination of the two, as reflected in M6, is better than either alone, indicating that each captures somewhat different aspects of student knowledge. Comparing M5, which includes socio-demographic data, and M6, which does not, we find that including socio-demographic data provides only a modest boost in performance. This is good news, as including factors like socioeconomic status to improve predictive performance would compromise the fairness of this approach. Although factors like socioeconomic status and ethnicity may be correlated with learning outcomes, there is no reason to believe that these are causal factors in determining these outcomes. Factors like pretest score and process variables almost fully account for any variance that would be accounted for by socio-demographic factors. The minimal difference between M5 and M6 demonstrates this point. We have used the proportion of variance explained by our models, or their R-squared values, to compare these models to those from previous work. We find that the proportions of variance explained by these models on held-out test sets are substantially larger than those reported in previous work. To drive some of this home with pictures, here are scattered plots of predicted values for the FCAT and FSA plotted against actual student test scores. But what about the hierarchical nature of our data? There should be at least some school-level variation that should be accounted for in these models. However, it is possible that student socio-demographic, process, and/or pretest data captures a lot of this variation. To consider this, we compare stepwise linear regression models to linear mixed effects models. In these models, we include all of the variables in the best stepwise linear regression model, plus a random intercept per school and a random slope for pretest per school. Better models might include student and/or class-level random effects, but given that students and classes don't persist from year to year, this would make generalizing across years more difficult in practice. We find that these linear mixed effects models outperform stepwise linear regression on models M1 through M4, but not on M5 and M6. Consequently, we find that a combination of pretest and process variables appear to be sufficient to obviate the need for a hierarchical model. Of course, the ability to predict standardized test scores is insufficient for eliminating them. High-quality analytics have to be embedded within effective instruction covering appropriate topics. Nevertheless, changes are happening rapidly. Legislation in the U.S. state of Georgia, for example, is focused on eliminating standardized high-stakes tests. The time is right for innovative approaches to assessment to take hold.
We believe Mathia is one form of that high-quality instruction, but it is worth taking some time to consider how poorly our current approach to assessment fits with what we know about student learning. As you have seen, Mathia's items are multi-step problems which model authentic mathematical problem solving. This contrasts with traditional standardized test items. In the context of classroom instruction spanning many hours, it is possible to ask students to complete problems that take up substantial amounts of time. The opportunities to do that in a 2 or 3 hour standardized test are much more limited. Also, since a standardized test is scheduled for a specific day, it makes sense for students to cram for test day. This is a successful strategy for passing the test, but an unsuccessful one for retaining knowledge. In dynamic testing, there's no cramming. The test is every day. We can also provide daily guidance on how students are progressing towards meeting end-of-course goals. Based on the predictive models we've described here, we developed an adaptive personalized learning score, applause, which customers now use to monitor student progress.
There are a variety of interesting open questions about the statistical approaches we've adopted, as well as those we have neglected in the current study. For example, we've used regression techniques rather than treating this as a classification problem. Further, it is possible that individual grade-level models would perform better than the omnibus approach we adopt, which includes grade level as a predictor of test scores. It is also unclear whether we are approaching the upper bound of predictive success we could expect to achieve. To establish this upper bound, we would need item-level test data, which were unavailable for the present study. There are also important practical questions about the nature of learning analytics systems that rely on these types of models for assessment. For example, as learners use embedded formative assessments, how do we communicate to stakeholders the evolution of predictions about performance over time? How do we communicate about the inherent uncertainty in these predictions? These questions and many others have come up as we developed the applause approach to progress monitoring and more generally have considered practical ramifications of this style of statistical modeling.
We have been addressing these questions and others in our latest work, but the task of changing the way assessment is done is going to require concerted efforts from many places in the learning analytics community. We welcome your input and collaboration in this task. Once again, thank you for allowing us to present at the conference from the less than sunny Pittsburgh. We look forward to seeing you at the conference next year.
Well, I guess we can still thank the speakers for having made this effort. It just seems that my session chair weapons are rather useless now. So we have 15 minutes that we can spend. There is, of course, no Q&A, but maybe still some of you has a comment that you want to share with the audience. Maybe you have had experiences with formative assessment yourself. Maybe you want to address some of these points that were mentioned there. So there should be some discussion of the paper if any one of you opts to. Yeah.
I came in a couple moments late, so I don't know if this was already addressed, and also haven't read the paper. But in the discussion, I didn't hear anything about their cross-validation process, and so what are the statistics on the generalizability of this model? Does anyone have any thoughts or knowledge about that?
So yeah, I guess the main idea, if I got them right, is to do the validation with the standardized tests that they would be using. So
I don't know the other speakers as well, or the other authors as well, but I am close with April, and it does not strike me as a step that she would skip, but I don't have direct knowledge, so yeah.
I guess I'll add in, I have seen a previous presentation of this work with more technical details, and there was certainly a cross-validation step. I don't know if I saw it in this talk, though.
Further comments, thoughts that you may have, maybe own things, yeah.
I was going to sort of raise a discussion point. I'm not in this assessment side of things, but it seemed like they were relying a lot on the existing tests as their litmus test of can we get close to what this is predicting for a student. And it seems like that doesn't seem like it's the way to go. It doesn't seem like it's going to really improve accurate assessment of student learning. If we can say, you no longer have to take this test, but we're still determining how well you can take the test if you were to do it. So I don't know if people had thoughts on that.
Maybe responses to that. I think I can partially see your point, because some of these tests have been just tailored so that you could test within a certain short time period, whatever you can do in that time period, while on the long run you are interested in in just different competencies of students that you could track in a formative fashion in a dramatically better way normally. So kind of trying to meet these test values is probably one step of actually seeing what you could do, but maybe just the first step, that would be my answer to that. But
I would say that just the work in general seems like it needs to go beyond that.
Further thoughts, comments?
Okay, I'll try and summarize the ramblings. Basically, the purpose in the paper seemed to be how well can we use regression to predict a student's outcome scores on the standardized test. How well can we use this system to match the standardized test? And if we have discussions of phasing out this standardized testing because it's not really assessing student learning, then why are we using the standardized testing as our gold standard for our analytics? I understand that, but I'm just saying, like, you know, as a body of research, I feel like we can go beyond that.
I agree with you entirely.
Yeah.
But one thing they did say is that they use the pretest as a predictor, and then they also use this tool and its output as a predictor. And when they combine the two together, they got a better score. So making the point that one is they're capturing information from one set of data that the other one's not capturing as well. So I guess the next step would be to investigate what is one capturing versus the other one not, to see if you can isolate what it is that is the real predictors that you could then base deeper learning activities or whatever around.
Yeah, definitely.
Further comments? Well, if that's not the case, then maybe someone from the Pittsburgh crew has taken some notes to hand over these questions or the discussion points to the authors. That would be nice. So I guess I'm collecting these. If there are no further points, then we have a break of 8 minutes in order to allow people who want to see the second presentation to actually see the second presentation. So we'll just have a short break and resume with the next paper after that. And we'll learn in the next two papers again, performance prediction, and we'll learn about 4CID and about FSQCA. So interesting things that are about to come up. Stay tuned.